Students, welcome to lecture number 6. So, today we will talk about convolution neural network, that is called CNN in short form. CNN is very important for image analysis. So, this is the course on deep learning and material science engineering. We will discuss from concepts to applications. Before that, let me just tell you something which very small portion of what I taught in the last lecture. Last lecture we discussed about regularizers in deep neural networks, right. So, basic thing about neural network is this particular slide where we have inputs like x1 to xn, multiply each of these inputs by weight factors or weights, then sum it over what is called a summation function, and then followed by application of a activation function. This provides you an output. Since artificial neural network is a parallel processing system, so hence this output of the network, what I have seen or is shown here on the slide, is then fed to the next network or next layer, and then calculations are done. So, what are these optimizers? Optimizers actually control the optimization of the process. So, this comes from the error analysis or loss functions. So, during any kind of a neural network operations, you are going to get error, and the basic idea will be to minimize the error. So, hence the error function or loss function needs to be optimized or rather minimized. Let us talk about that. Any DL actually requires that. So, if I have a f as a scalar valued functions in x and looks like this. So, you could clearly see there are many maxima and minima. So, there is a local minima here, there is another one there, there is another one there, and this is the global minima, right. Similarly, there are two local maxima here and then here, and there is one at the here, which is called the global maxima. So, these functions mostly has one or more maxima, minima, or maybe even saddle points. So, we would like to find out the absolute minima, right, then only you can minimize the errors. So, how do you do that? Basically by applying gradients or derivatives, right, we talked about it. The magnitude of derivatives at any point tells you rate of change of the function with respect to the variables at that point. Now, derivatives in these points you could clearly see will go to 0, right, because the curve becomes flat at this point, you can clearly see that, right. So, hence we can use the derivative or the gradient as a means to calculate or find out the maximum minimum points. And these derivatives, most of these deep learning methods, whatever we learn, will have complex functions or maybe functions or multivariate functions. So, there you have to use different rules of derivatives. Now, let us talk about little bit saddle points. As you can see here on the right side, you have a local minimum here or minimum rather, you have maximum here. The saddle point is this, just like when you go for horse riding, you sit on a saddle, like that is exactly what it is. So, points where derivative is 0, but they are neither minima nor maxima. Such a kind of points also exist. Let us look at that. So, these are your maxima and minimum points. There is another minima here also. This is what is your saddle point. Curve has flattened out, but this is not a maximum minima point, right. So, these are called saddle points. So, saddle points also derivative will go to 0. That is the problem actually. When a multivariate functions, saddle points, maxima, minima, everything will have derivatives to be 0. How to find out what is the minimum functions? Okay, and these saddle points are very common in loss functions of deep learning methods. That is why we need to handle these optimizations very carefully. That is why the second derivative or higher derivatives comes handy. They can allow you to find out that. But as I said, the deep learning uses many complex data and large number of variables or many kinds of features. So, hence this loss function will be multivariate functions. This is one such multivariate function. You can see here x1 and x2 are the two variables, and this is what is your f, right, which is a function of x2 and x2. So, now there are many points here, minima, maxima, you can see here, right, maximum points are here. Am I clear? So, hence if I take a projection on the top, it looks like this. How to find out that? So, let us okay, this also can be handled by using gradients or derivatives of multivariate functions, right. So, for a multivariate functions, derivative is defined like this, okay, del f by del x1, del f by del x2 to del f by del xt, when R is a basically a d-dimensional function of x, right, it's x goes to x1, x2, x3 to xd actually. So, for saddle points and the optimum functions again can be defined like a one dimensional case like single dimensional variables, but second derivative in this case is that is what is to be measured or calculated by Hessian. This is something different. What is Hessian? Hessian is nothing but a matrix of all the second derivatives. So, you have seen how we are taking the second derivatives. It is a t-dimensional space. So, you have x1 to xd actually as a variables, x1, x2, x3 go up to xd, right. These are variables and your function is f. So, you take double derivatives like this shown here, okay, and put in a matrix format. That is what is called a Hessian. Hessian matrix can be used to access or assess the optimal saddle points. If the first derivative goes to 0 and second derivative is positive, that says Hessian is positive, then we can talk about that x is a minimum, that particular x. If first derivative is 0, second derivative is negative, then we can call it as a maximum. So, you understood, right, how we can handle multivariate functions, how we can find out the optimum points. Now, we also discuss about non-convex and convex. Convex functions are easy to handle because they have a optimum 0 or say optimum minimum value here, okay, same thing shown here in the loss function, but non-convex functions can have local minima, right. That is where the problem begins, how to handle that. So, we have to first find out which are the convex or which are the non-convex functions. So, as you say, convex functions are basically having, if I draw a chord like that, all the points of the convex function between these 2 points x1 and x prime are lying below the chord, okay. But on the other hand, for the non-convex functions, that is not the case. So, that is why you have to use Jensen inequality. The chord lies out the functions. That means that if I define alphas, alpha 1 to alpha n, and sum it over alpha, that is equal to 1, addition of all alphas. But important aspect is if I multiply alphas with the x and get the function value, that must be less than equal to alpha fxi in the range 1 to n. So, first order convexity is what can be used. Second order derivative Hessian must be positive semi-infinite, okay. So, that means even, so we can find out that convex function. If it is not convex function, then we have to do a Hessian problems little bit different way, it will be difficult. So, that allows you to provide you the method called gradient descent, okay, which very simple. If I take a gradient, put it 0, and if we solve all the w's, it is a closed form solution, but it does not happen. then it becomes a problem, or it becomes a difficult issue. So we use gradient descent, and it's iterative optimization functions. And what is it? It tells you that if I take a derivatives of w, I have already told you in several lectures, of the loss functions, this must be 0, then you can find out all the w's which are optimized, right. So gradient descent algorithm can be discussed this slide. This slide is for you to learn. So here you can see it's nothing but a technique which can be used to find the best solution of a problem by making small adjustment in the right directions. What does it mean? It means to find the lowest point here, you can see here, of a hill area by walking down the slope step by step until you reach the destination. Okay? So that means you have to find out the slope, and slope is what is important, or gradient what is important, right. So what do you do? First you go to the top of the hill. That means you could start with some random guess for the model parameters. You may have some idea about the model, but if you don't have, you can start with a random guess. After that you have to feel the slope. That's why you have to calculate the gradient, and gradients will tell you which direction you should move. So therefore you need to travel along the steepest downfall. Why? Because then only you can reach the minimum point quickly. So bigger the slope, bigger is the step you can take. And this step 4 is nothing but repetition of step 3. So model will be learned and minimize the error. So therefore gradient descent in a nutshell moves toward the bottom of the minimum, of the loss functions, and that's what you want for every step in the neural networks, right. So this is something shown here. You start with some initial values and they calculate the slope. Slope is negative, move these directions. Again you calculate the slope here, slope is negative, move this direction. Again you calculate slope here, like that till you hit the minimum point. Okay. So the step size, what you are checking here, change the step size, what is known as a learning rate. And learning rate is what? It's basically nothing but a step size, I told you. So learning rate must not be very high or very small. If it's too small, it will take a large number of steps to reach the minimum. If it's too large, sometime you may miss the minimum value and diverge, right. So that's why you have to take a good learning. There's no necessity to keep the learning rate fixed throughout the learning process also. You can even keep on changing also based on this. You can see here, or based on this, you can change that. Okay. So initial weights are basically what you guess, and using this learning rate you can optimize that. And as I told you, if you use a very small learning rate, it takes you a long time to reach the optimum value. If you use a large learning rate like this on the right side here you see, then you can miss even your minimum point. Am I clear? Two important aspects to remember. First, you should check your function which you are using for the gradient descent, is it differentiable or not. If it is not differentiable, you cannot calculate the gradients. So therefore we cannot find out the direction of the steepest descent. And convexity is very important. If it is convex, it is easy to find out the minimum. If it is not convex, then you have to use the typical methods I discussed with you. So I will not talk much about that. Let me go to directly to the CNN. Okay. So I have shown you some example. Okay, I will not go into details of that. You can look at it from my previous literature just to show you how it can happen. Okay, you can reach the optimum functions, so you can follow it up. There are many variation of this process like stochastic gradient descent method, minimax gradient batch descent method, or a SGD, stochastic gradient descent with the momentum methods. Okay. So let's coming back to the convolution neural network. So convolution neural network, or CNN, it is famous to be known, is basically architecture inspired by human visual system, the way we visualize things, and it is designed to process images by capturing spatial relationship between the pixels, correct. So let me just tell you that. So this is a spatial deep learning method, and you must master the CNN. So we will discuss slowly and one by one so that you can understand it very nicely. So, it is a special deep learning algorithm primarily designed to classify and process the visual data like images or videos. And we mimic the human visual communication technique to mimic that. CNNs automatically learn to recognize the patterns and recognize pattern by edge, this, or you can use textures, or you can use objects, okay, so that you can do without any much error. So, but this all depends on how does a computer see image. Human, we are trained, right? Our way of recognizing image. If you see an image, you can immediately recognize as a bicycle or a car or a train or a bus, right? Because you have been told at the beginning of your life that this is what is the bicycle looks like. This is how the bus looks like, right? So, you can immediately see and recognize that. How do you recognize? By looking at the features, right? Bicycle has two wheels and it is a, you can drive it also, right? It has spokes. Similarly, cars will have different kind of look, features. But if you want to first do that, first you have to understand how computer capture or see an image. I am showing you one of my image, okay, and it is a color image you can see, but how does the computer see images, okay. So, let me just go to the board and explain to you. So, computer sees an image as a matrix of numbers. Computer is not like a human, its image as a matrix of what is that? Very simple. You can have two kinds of images, grayscale or black and white, right? We call grayscale, and many people call also black and white images, but grayscale is what is the scientific word. So, what do you do? This represents two-dimensional grid, right? Two-dimensional grid, okay, or two-dimensional images. By the way, images are represented by small element called pixel. That is nothing but a picture elements. When you buy a mobile camera, you always look at the pixel, 12 megapixel, 15 megapixel, 14 megapixel or maybe 50 megapixel camera, right. So, this pixel is what is your picture element. So, any image you can divide into small parts, and each of these parts like this I can divide, right. So, this is called a pixel. In video we call a voxel, video element, voxel, okay. That is called a video element, but let us talk about the pixel first. So, in a grayscale image, we can represent each of these elements. So, this is like a two-dimensional image. So, you have y and x, right. So, if I draw all these pixel, I will draw few of them to show you. Okay. So, we can define each pixel by center, coordinate, right. Coordinate of each pixel can be defined by x, y numbers, right, that is like a coordinate geometry. And in addition, each element will have also brightness. Since it is a black and white image, we can define the intensity or brightness as a factor, right. And we have a brightness scale. It starts with 0 and goes to 255. 0 stands for white or black, sorry, black, this cannot be white. 0 stands for black, complete black. 1 and 255 stands for white, right? That is what it is. So, that means each element I can give a number depending on intensity of the element, right, either 0 or any other number between 0 and 255 depending on the intensity. So, hence each element will have 3 coordinates, one x, other one is y, and obviously the intensity or brightness. So, that means if you have a black and white image 12 megapixel, right. So, that means what, 12 into 10 to the power 6 pixel, and each element has 3 coordinates. So, total number of thing is 3 into 12 10 to the power 6 elements. So, that is what is the total number, right. Computer will see that way. So, computers will see this as a matrix of numbers. So, this is the number, it is a massive number, right, huge. Think about it, if you have a 100 megapixel camera, then what will be the number? So, that is like a large numbers. So, that is for the grayscale image, okay, that is black and white. Nobody uses black and white image except you change the image to black and white and show it. What about color images? What happened to color image? So, color image has colors, right, built in, and in the you can see the slide, my own picture is a color image, right. So, color image is basically represented by 3D grid. You understand 2D grid, here we are talking only about intensity, right, nothing else. So, if you know the intensity, you can find out what grayscale the image is. And for a color image, we use 3 basic colors: red, blue, so green and blue. We call it RGB, right. So, every element we must have intensity of red, intensity of green, intensity of blue, every element whatever. So, every element like what have I drawn, other than x and yi, you have to have a RGB scale. Let us like this intensity, because this blue and that brightness will kind of create problem. So, this is for the grayscale xi, yi and I. So, for a color image you have not only xy coordinates x and y, yi, other than that you have also red, blue and green RGB. Okay. So, that means what, you have xi, yi, red, green, blue. Every pixel will have 5 elements to be stored. That means you need to have 5 element data. So, that means here for 12 megapixel camera you will have 5 into 12, 16 into 10 to the power 6 elements, matrix of data for the whole image. That is a massive number, right, 6 into 10 to the power 7, right, you can calculate that. So, 12 into 10 to the power 6, and each element, this is the pixel element, each element has 5, 1, 2, 3, 4, 5. So, 5 into 12 is 60. So, that means what, 6 into 10 to the power 7, that is quite large, almost 6 billion, right, oh, more than that. Anyway, so that means what, this is the amount of information you need to store, and computer sees as a numbers, matrix of numbers. Let us come back to here, that is what I show in this slide. This is my image, and that is what, if I make it black and white, that is what you see. The hair will look black, right, that is why you see black, and this region, beard or mustache also will look like black, specs also is a little bit blackish, So, these numbers you see here, they are very close to 0, maybe 10 or 7 like that, and these numbers which are high, 200 something, 297 here, 238 here, 237, 238, they are all 214 here you see, they are very close to 255, they are white. So, you do that. So, image is just a matrix of numbers. So, for 1080 into 1080 image, this is nothing but a 1 megapixel. Okay, 1 megapixel is 1080 images, 1080 pixel elements, that will have this many into multiple 3 elements to be stored, right. So, question is, can I just do classification on these 11 million long image vectors directly? Each one is image vector, right? Answer is no, we cannot do that. Your computers cannot handle it, right? Then use something else like patches or build them up very slow, step by step. So, before I do that, let me just explain you how does the human animal brain works. So, classically this is our eye in a nutshell shown, you have a retina and you have a lens. So, this is your actual the object from where the radiation comes, and then the lens focuses and creates an inverted image, and the inverted image is sensed by the optic nerve and then you can feel it. So, question is, can you basically change that? Okay. So, you can see here in the optic nerve basically you have ganglion and bipolar cells, right, that basically senses the image. So, we can think of creating such a kind of structures in using neurons, right, that is what you can do. We can have pixels, edges, shapes, primitives or even scenes like in videos, and we can build that. So, layers of 4 layers correspond to bands with respect to the slants, contrastic edges, you can create that, right. That is how we can actually mimic this human visualizing way in case of CNN. So, before that I think we should know what is CNN, okay, that is very important to know. But let me just tell you something about neural network, then we can come back to it, because we have to finish this part of the lecture 6, I will come back to second part. Since we are connecting neural network, right, so you can always think of neurons as basic unit. Right. So, what do? You have inputs like basically x size. So, then you write z is equal to xi wi plus some bias apply it to a activation function, that is what you do. That activation function will gives you output, right. Am I clear? So, this is your input, are basically x size, and then you can have hidden layers. These layers are between input and output. Each neuron in each layer is basically summed the results of the neurons in the previous layers, and then finally you have output. You can have many human hidden layers. Am I clear? And output is nothing but the calculation output. Okay. So, now question is, why do we use this convolution and how do you use the convolution? That is what is the question is. Okay. For that you to first understand what is convolution and how does it done mathematically. Then you can get back to you how it is used in CNN. So, that is what we will discuss in the next part of lecture, what is convolution and how it is calculated.